Hi everyone. So in this video, we're going to be covering something called the net change theorem, and then we're also going to be introducing the concept of an indefinite integral. And you'll see that these two topics are actually pretty separate and distinct from each other, but your book just kind of happens to lump them together in one chapter. And I thought about doing two separate videos, but indefinite integrals there's really not too much to say about them. So I figured I'll just go with what the book does and kind of lump this all into one video. Okay, so the net change theorem is basically a statement that allows us to interpret FTC2 in terms of real world situations. So just to remind you, what does FTC2 say? So again, FTC stands for Fundamental Theorem of Calculus. 2 is part 2 because part 1 was that more kind of conceptual statement about taking the derivative of an area function. So FTC2 just says that if you're trying to integrate a function from a to b, that how you can actually calculate that value is by taking any antiderivative of the function on the inside, the integrand, and evaluating it at b, and then evaluating it at a and subtracting the two. So again, f of x is any antiderivative of little f. And as we talked about in the previous video, there's really no reason to choose an antiderivative with a c value other than 0. So you're just kind of picking the simplest antiderivative to work with. So there's a different way of writing this that I just think might be helpful in helping us kind of understand how the net change theorem works. So this can also be written as so because capital F is the antiderivative of little f, that means that the derivative of capital F is little f, right? So instead of writing little f of x inside, I'm going to write capital F prime. And I'm not really saying much here. All I'm doing is kind of rewriting it just to emphasize the fact that the function on the inside is the derivative or the rate of change of the function on the outside. So let's look at an example of a situation where we have a kind of a real world rate of change and kind of try to interpret what that would tell us in terms of evaluating the integral. So let's say that we had a function h of t gives the height of a ball after t seconds. Then what does that tell us? Well, if we take the derivative of the derivative of h of t, we get h prime of t. That's the same as the velocity, right? So thinking back to Calc 1, you know that if you have a function that tells you the position of an object, so height would be one type of position function, then its derivative is a velocity function. So h prime of t is the same as v of t, the velocity function of the ball. So what would it mean to integrate the velocity function? So if we were to take the integral of a velocity function from a to b, well, based on what we wrote above here, if we have a derivative on the inside, then the original function will end up being what we're evaluating on the outside, right? That's how the fundamental theorem of calculus works. So we would end up with h of b minus h of a. So how could we interpret this in terms of, like the height of the ball and what's going on? Well, this here would represent the height at time b, so whatever that value was for b, and then this here would represent the height at time a. And so if you subtract the height at time b minus the height at time a, that's going to give you the change in height from t is equal to a to t is equal to b, right? So there's a word for this idea of if you have some kind of position function, whether it's a height function or maybe a function that says the position of an object that's moving along a straight line, or any kind of position function. If you're looking at the change in position between two different times, the word for that is something that's called displacement. And we'll talk a little bit more about this in a few minutes when we get into a more specific example. So displacement doesn't mean the total amount of distance traveled. It just means the difference in the distances. So just again, the subtraction of the in this case, height at one time minus the height at another time. So I want to go back up to this and just kind of add a little bit more detail to what's going on here. So basically what I want to add here is that, so basically if you're integrating the rate of change of a function. So again, that's where we have this inside our integral. If you're integrating a rate of change of a function, the result is what we'll call the net change in the function. And then net change just basically means, how much did the function change between the two times that you're plugging in. So that's really all the net change theorem says. It just is a way of describing what's going on with integrals in the context where you're talking about rates of change. So, so far when we've been integrating, we haven't really been interpreting what our functions mean, right? It's just been like, oh, here's some function f of x. Now we're saying if f of x specifically represents some kind of a real world situation, and you're integrating the rate of change of that real world situation, your result is going to be the change in the original function. So again, one example of that is here. The velocity is the rate of change of the height. And so when we integrate the velocity, we get the height at one time minus the height at another time, which is the change in height. So let's look at one more kind of general example, and then we'll get into one where we'll actually have a specific function and we'll talk about what the word displacement means. So let's suppose, again, we have some kind of a function, and this time we have a function v of t that gives the volume of water in a reservoir after t hours. Do I know how to spell reservoir? Let's see. Hopefully that's right. So what would the derivative of that represent? So v prime of t, and again, just to be sure, I'm not using v of t to represent velocity here, right? So hopefully that's not too confusing. Up in the integral above, we use v of t to represent velocity. Now we're using it because v is for volume, right? Sorry, having a lot of issues right now with my touch screen. There we go. So what would v prime of t represent? Well, it would represent the rate of change of the volume of the water. And in this case, like, how would you maybe explain what that means, the rate of change of the volume of the water? Well, you can imagine that water is either kind of flowing in or out of this of this reservoir. And so that's really what we're talking about. So another way of saying that would be the rate at which water is flowing in or out. Okay, so what would be the meaning if we were then to take the integral from time A to time B of this rate of change? Well, we would get V of B minus V of A. And so V of B would mean the volume at time B. And V of A would mean the volume at time A. And so what does it mean to subtract them? It would tell you how much did the volume change between time A and time B. So this would be the change in volume from T is equal to A to T is equal to B. So that's really all the net change theorem says. It kind of just makes sense, right? It's just a way of rephrasing what we've been talking about, but with a little bit more now kind of a real world meaning. Okay, so I think kind of the most interesting or most complex way of talking about the net change theorem is this idea of when you have a position function and you're trying to find displacement, because there's this difference between the idea of displacement and total distance traveled. And that's what I want to talk about now. So we're going to be talking about displacement versus total distance traveled. Okay, so when I teach this class in person, I like to actually walk this out in front of class to really demonstrate, but I'm just going to kind of write it down in words. So let's say I walk 5 feet forward, and then I turn around and walk 3 feet backward. So what is the total distance I've traveled? Well, I've traveled 8 feet, right? Because I walked 5 feet forward plus 3 feet backward. So my total distance traveled would be a total of, 5 plus 3 is equal to 8 feet. But that's not the same as displacement. So we talked about on the previous page how displacement is not about how far an object has traveled in that time. It's about the change in position. So the displacement, which we can think of again as the change in position, well, that would not be equal to 8, right? That would actually be equal to, so we would take the 5 as being 5 in the forward direction, but then because the 3 feet is backward, that actually counteracts the 5. And so we would actually subtract the 3, and we would find out that your displacement is 2 feet. And let me actually draw kind of a diagram to represent this. So what I'm saying here is that, so let's say I'm walking, here's my starting point, and I walk forward by 5 feet. And then I walk backward by 3 feet. Well, that means that once I'm done walking, I'm standing right here, right? And so I'm only a distance of 2 feet from where I started. And so that's what displacement means. It's basically where is the object in comparison to where it started, which is the same as thinking about how much its position changed from the starting point to the finishing point, right? So my change in distance was only 2 feet, even though I actually walked a total of 8 feet. And sorry, I'm going to make this clear because this kind of looks like it says 8. So this was 5. Okay, so let's now look at an example, and we'll basically see that as we saw on the previous page, integrals are really best for finding displacement, and if we want to find the total distance traveled, we have to do a little bit of extra work. Okay, so let's say that we have an object, and I guess we'll call it a particle. So a particle is moving along a line. And it has a velocity of v of t is equal to t squared minus t minus 6. And let's say that the time is being measured in seconds. And seconds, sorry. And distance is measured, I'll say position is measured in meters. So the units for the velocity are meters per second. And by the way, why, like you'll notice this coming up in a lot of these problems, they'll often say that a particle is moving along a line. And the reason for that is because we're not really equipped with the tools that we have in this class to talk about the velocity or acceleration or anything like that for an object that is moving in more than one dimension. Because we're really just kind of recording what is the position in one direction as time goes on. And that therefore we have the velocity, again, relative to just that one direction as time goes on. And so it's the same thing with like the ball and the height. If you're just measuring the height of something as time goes on, you're not paying attention to whether it moved sideways at all. You're just recording the height. And so similarly here, it's the way we can make this kind of the most simple is just to say, okay, we just have a particle moving along a straight line. So truly, as we measure its position, that's really the only direction that its position is changing. All right, so the first thing that we want to answer is, actually I have these pictures in the wrong order, so let me put this one up first. So this is a graph of the velocity. So actually, before we get into the first question I want to answer, let's think about what this velocity graph kind of tells us. So one thing that's really important to remember from Calculus 1 is that when the velocity function for an object is negative, that means that the object is moving backwards. And when the velocity function for an object is positive, that means that the object is moving forwards. So basically in this graph, in this whole portion, so from t is equal to 0 to t is equal to 3, the object is moving backwards. And I think it's really easy to get confused because you look at the velocity function and you start to try to interpret it as motion. This is not a picture of the motion of the object, right? This is a picture of the velocity. So for example, the velocity at 1 second is -6 meters per second, and that means that the object is moving in the backwards direction at a speed of 6 meters per second. And after 2 seconds, the velocity is -4 meters per second, so the object is still moving backward. And then at time is equal to 3 seconds, then the object is momentarily paused. So it's kind of switching from going backwards to going forwards. And so after 3 seconds, now the object is moving forward. Okay, so the first question I want to ask is, what would be the meaning of, so what would the integral from 1 to 4 of this velocity function, I'll actually write down the function, so it's t squared minus t minus 6 dt tell us? What would it tell us about this object? So as we talked about on the previous page, it would give us the displacement. So why would it give us displacement rather than the total distance traveled? Well, because when you take an integral, it's counting the area that's under the x-axis or t-axis in this case as negative, and it's counting the stuff above the t-axis as positive. And so what's going to happen is, just like in this diagram that I drew up here, the negative and the positive are going to cancel each other out, and you'll just be left with what's the difference in the position. And so this will give us the displacement from t is equal to 1 to t is equal to 4. So again, like really just to emphasize it here, it's basically because this area is going to be negative and this area is going to count as positive. So when you do the integral, just looking at the picture, it looks like we're actually going to get a negative number overall because the object spent more time moving backwards than it did forward. And so we'll have overall a negative displacement, which means that the object will be behind its starting point. So let's actually evaluate this so that we have a number to then kind of compare when we do the next part. So if we were trying to take the integral from 1 to 4 of this function, and maybe let me go down here actually. So the integral from 1 to 4 of t squared minus t minus 6 dt. So we just need to find the antiderivative. So that would be t cubed over 3 minus t squared over 2 minus 6t. And then we want to evaluate this at 4 and at 1. So going to be a little bit of annoying fractions here, but you probably noticed if you did the worksheet from yesterday that, there were definitely some annoying problems in terms of the fractions. We're not going to be doing problems like this all quarter, but it is important that you are comfortable working with fractions. That's definitely just one of the things that comes up in Calc 2. So for the first part, we get 4 cubed. So that is equal to 64 over 3. And then we have t squared, which is 16 over 2. And then we have 24. And then from that, we subtract plugging in 1. So that's going to give us 1/3 minus 1/2 minus 6. So altogether, here we're going to have 64 over 3 minus, 16 over 2 is 8. So that's minus 32. And then here we'll have minus 1/3 plus 1/2 plus 6. So let's make a common denominator with everything. I guess first maybe let's combine these two fractions that both have thirds. So we have 63 over 3, which actually, I think 63 is divisible by 3. It is. It's our lucky day. So we're going to have 63 over 3, which is equal to 21. And then we have minus 32 plus 6, so that is equal to negative 26. And then we have still this plus 1/2. So this is going to be, like I said, 21 minus 26 plus 1/2. So that's equal to negative 5 plus 1/2, which is equal to negative 4.5, right? Or negative 9 over 2. And so what are the units of this answer? Well, the velocity was given in meters per second. And so that means that the units for distance or position or displacement are going to be meters. So that just means that compared to where it started, or compared to where it was at 1 second, 3 seconds later at 4 seconds, the object is negative 4.5 meters behind where it started at 1 second. Okay, so that's displacement. So what if we wanted to figure out the total distance traveled? So going back to this example here, how did we figure out the total distance traveled? Well, we added up the distance traveled in the positive and the negative direction. We basically treated them both as positive, right? Even though technically this part, the 3 feet, that was in the negative direction. And so when we found the displacement, we subtracted it. In order to find the total distance traveled, we treated it as positive. And so that's basically what we need to do. We need to add up both of these areas as positive areas. because really this blue part is the total amount of distance this object has traveled going in the backward direction, and the green area is the total amount of distance it's traveled in the positive direction. And so we need to just add those both up as positive numbers. So one way of doing that is actually to take the absolute value of the function. So let me kind of summarize what I just said out loud, which is, so how could we find the total distance traveled from t is equal to 1 to t is equal to 4. So basically, we need to count all of the distances as positive. All distance as positive. And so basically what that means, basically taking that blue area above as positive instead of negative. And so one way that you can kind of communicate that idea of counting all the area as positive is you can take the absolute value of your function, right? Because when you take the absolute value of a function, that has the effect of flipping anything that used to be below the x-axis, or the t-axis in this case, to be now above the t-axis. So if we take the integral from 1 to 4 of the absolute value of t squared minus t minus 6, that will give us the total distance traveled. Because now if we look at this picture, we're now including the part that used to be below the t-axis is now above the t-axis. So now this area is going to be counted as positive, even though it was originally backwards. And this will also be counted as positive. So unfortunately, there isn't really, like a special formula for evaluating the absolute value of an integral. You could kind of think about absolute value as making some things positive and some things negative. Like that there is basically a way to kind of take this integral and transform it into a new set of integrals. But personally, I think the easiest way to actually evaluate this integral is just to draw a picture and figure out what part is positive and what part is negative, and just make sure that the part that was originally negative is now getting its sign flipped. So we're going to kind of ignore the absolute value bars, and we're going to do the integral from 1 to 4 from 1 to 3, because that was the part that was originally negative of this function. Sorry, I keep saying minus 6t when I mean minus t. And then I'm going to put a negative sign out front because we know, looking at this original picture up here, we know that this is going to come out to be negative, right? If we just do the integral from 1 to 3 of the original function, we are for sure going to get a negative number just by looking at this picture. And so if I put this extra negative sign out front, that's going to counteract the original negativity and now give us a positive result. So this is basically, this negative sign here is in order to make the area positive, because two negatives give you a positive. And then we'll add to that the integral from 3 to 4. And that one we don't need to switch the sign because it's already positive. Okay, so let's see what we get for these. So basically, again, we're just going to be evaluating the same integral, but now we're flipping the sign of one of them. So for the first part, we have, again, t cubed over 3 minus t squared over 2 minus 6t. evaluated at now 3 and at 1. And then once we get that answer, we're going to take that answer and make it negative. Or not make it negative, but flip the sign. And then to that, we're going to add the same antiderivative, but now evaluated at 3 and at 4. Okay, so what do we get in this case? Well, we get t cubed is 27, so we have 27 over 3. And then we have 3 squared is 9. And then we have 18. And then from that, we have to subtract the lower bound. So be really careful. I think one of the easiest ways to make mistakes, and I probably mentioned this in the previous video, but there's a lot of negative signs in this problem, right? And a lot of sort of parentheses to keep track of. So that's, again, probably one of the easiest ways to make mistakes. Okay, and then to this, we're going to add now basically the same thing we got the first time. So that was 64 over 3 minus 16 over 2 minus 24. And then from that, we have to subtract t squared over 3. So that is going to be 9 over 3. Or sorry, this was supposed to be cubed. My bad. So it's again 27 over 3 minus 9 over 2 minus 18. So a lot of numbers to deal with. Let's see how this all pans out. So I'm just going to start by distributing in the negative sign so that we can kind of clean everything up. And sorry, I put this extra t there. That wasn't supposed to be there. Okay, so we have negative 27 over 3 minus 9 over 2 minus 18 minus 1/3 plus 1/2 plus 6. And then over here we have 64 over 3. We have minus 8, minus 24. And then if we distribute this negative sign in, we get minus 27 over 3 is 9. 9 over 2 is going to become positive. And then we have plus 18. Okay, so still have to clean this up a little bit. And actually here, let me simplify that. That was 27 over 3. Let's make that a 9. Okay, so now we have negative 9 plus 9/2 plus 18 plus 1/3 minus 1/2 minus 6 plus 64 over 3 minus 8. And actually, let's maybe start to combine these numbers. So negative 8 minus 24 is negative 32, minus another 9 is negative 41. And then actually we can add this 18 on too. So negative 41 plus 18 is going to give us negative 23. And then we still have this plus 9/2. Okay, hopefully I haven't made any mistakes. It's definitely possible that I did. But let's try to start combining some things that have the same denominator. So we have a 9/2, a negative 1/2, and another 9/2. So altogether, that is going to give us a, so that's negative 8/2 plus another 9/2. So we have 17/2. And then we have 1/3 and we have 64/3. So together that's going to give us 65/3. And then for the actual just integers, we have these 4. So let's see, we have negative 9 plus 18. That's going to be 9. And then 9 minus 6 is 3. And then 3 minus 23 is negative 20. So altogether, we want to make a common denominator here. So we want to make a denominator of 6, right? That would be our least common denominator here. So we need to do 17 times 3 to get that common denominator. So that's 15 over 6 plus, and then we do 65 times 2. So that's going to be 130 over 6. And then this would be negative 120 over 6. And so altogether, our answer comes out to be, so 51 plus 130 is 181 minus 120 is 61 over 6. And again, our units are meters. So definitely, again, some annoying arithmetic to do, but the main thing I just want you to understand is really the concept here, this idea of to get the distance traveled, we need to make sure everything's positive. And really, really, I recommend when you're doing these problems, I know that for some reason students feel very, I often find that students are hesitant to draw pictures. Like maybe you think it's faster or easier to not draw a picture, but I just think it helps your understanding so much if you just draw the picture. And I think in this case, it'll just make your life so much easier to figure out what's the positive part, what's the negative part, if you have that picture in front of you. Okay, so that's it for net change. I'll put some other questions like this on the worksheet for today, so definitely check those out. But then the last thing I want to talk about is the idea of an indefinite integral. So like I mentioned earlier, indefinite integrals, there's really not too much to say. We'll see that it's basically just a new notation for something we already know about. So definite integrals are basically what we've been talking about so far recently in this class. So definite integrals are when you have an integral from a to b of a function. And basically what do definite integrals give you? They give you a number, right? When you evaluate a definite integral, you should always get a number. So I'll even just write that equals number. And what does that number mean? It's basically, I'll say area in quotes. It's really not, I've mentioned this a few times, area is probably not the best word to use because area is technically supposed to be positive. When I say area here, I mean, counting some area as positive and some as negative. So what is an indefinite integral? An indefinite integral is basically when you have an integral symbol, but you don't put any a or b on it. And so what does that mean? It's basically just a symbol to mean find the antiderivative. So what are you going to write down? You're actually going to write down a function. Your answer should not be a number, it should be a function. And what is that function specifically? That function is going to be the most general antiderivative of f of x. So it's really just a new symbol. It's like going back to what we were talking about the very first video of this quarter, finding antiderivatives. It's just that now we have a symbol for it. So let's do a few examples. So for example, if you were asked to find the most general antiderivative of e over 1 plus x squared. So what's going on here? Well, you should recognize that 1 over 1 plus x squared is the the derivative of inverse tangent, right? So the antiderivative of 1 over 1 plus x squared is inverse tangent. So what's going on with this e? Well, notice it's not e to the x. There's nothing. It's just literally the number e. And so this is actually the same as if this was like 5 over 1 plus x squared, right? So whenever you see a problem where there's an e and it's not e to the x, one thing to do if you get confused is just literally replace it with like a different number, like 3 or 5, and think about what would you do in that situation, and then you're just going to do the exact same thing but with e, because e is just a number. So one thing that we talked about when we talked about properties of integrals that I want to kind of re-emphasize because it's really important is that when you have a constant, you can pull that constant outside of the integral. So I can rewrite this as e times the integral of 1 over 1 plus x squared. So why would you do that? Well, now you can just focus on, what's the antiderivative of this function, and you don't have to worry about that extra number. And so we know that the most general antiderivative of 1 over 1 plus x squared would be inverse tangent of x plus c. And so now you can just multiply that e in, and basically you don't have to write e times c, right? You can just say plus c, because c is just supposed to represent any constant. So it doesn't really matter that you multiply it by e, because it's not one specific constant. It's like a stand-in for any constant. And one other thing I just want to mention here that I feel like I should have mentioned at some other point and I forgot. So let's say that instead your integral looked like this. So what would that mean? That would just be a shorthand. So whenever you see an integral where there's like a dx in the numerator, that's just the same thing as saying the integral of 1 over 1 plus x squared dx. So you'll see that notation being used sometimes. It's just a way to kind of make the integral more compact. So whenever you see a dx in the numerator, if you want, you can just replace it with 1 and move the dx down. So that would just be, again, inverse tangent. Okay, couple more examples. So let's look at now the integral of sine of theta over cosine squared of theta d theta. So this is an integral that we'll actually learn a new method. So maybe just to give you an idea of what a lot of the next couple of weeks are going to be like, we're basically going to be learning all sorts of different methods for evaluating different types of antiderivatives. So far, we really only know how to do simple antiderivatives. There are certain ones that we just kind of know, oh, okay, this is the derivative of that, so this must be the antiderivative of that. So coming up, we're going to be learning how to kind of tackle more complicated functions and figure out their antiderivative when it might not be so obvious what that antiderivative is. So we will be learning how to deal with things that look like this, actually starting in the next video. But in this case, there's actually a different way to do this. So you might look at this and say, that's not a familiar derivative, so I don't know what the antiderivative is. But if we start by rewriting this in a more, breaking it basically into other trig functions, we'll be able to see that we actually do know the antiderivative. So we can rewrite this as sine of theta over cosine of theta times 1 over cosine of theta, right? That's the same thing as what we had written previously. So how else could we write that? Well, sine of theta over cosine of theta, that's the same thing as tangent of theta. And then 1 over cosine of theta, that's the same as secant of theta. So this is maybe not one of the ones that is kind of first on your mind, but this is actually one of the antiderivatives that you should be familiar with. So tangent of theta times secant of theta, that is the derivative of secant of theta. And so our answer here would be secant of theta plus c. All right, we'll do one more example and then that will be it for this video. So let's say now that we wanted to take the indefinite integral of x plus 1 times x minus 1 dx. So we're just trying to find the antiderivative. So in some cases, and this is in some ways kind of actually like the previous question, there's something that you need to do with your integrand before actually finding the antiderivative. So what would not be correct here would be to individually take the antiderivative of each of these and then multiply them together. It just does not work that way. Why does it not work that way? Well, there's this thing called the product rule, and when you're taking the derivative of a product, it's not just the product of the derivatives, right? You have to apply the product rule. And so when you have a product inside of your integral, we'll see later on in the quarter that there's kind of like a reverse product rule that you can use. But you don't even have to do that in this case because you can just multiply these two things together, right? So you can multiply together x plus 1 times x minus 1, and you get x squared minus 1 dx. And so our antiderivative is going to be x cubed over 3 minus x plus c. So one last thing I just want to quickly show you is that, like I said, we'll be spending a lot of time in this class learning methods for taking antiderivatives of more complicated functions. So On tests, I will be giving you a table that kind of looks like this, that is basically just the basic antiderivative rules. These are rules that I think it's probably good to have memorized just for convenience sake, but I will give them to you on the test just so that, there's no chance of you not getting these basic building blocks. And the reason for it is because, like I said, most of the integrals we're going to be doing are not just going to be these simple integrals. They're going to be ones where there's more of a process involved to figuring out what the antiderivative is. And so I'm basically just going to kind of give you these building blocks so that when you have a more complicated integral, you'll go through the process of breaking it down, however it needs to be broken down, but then you can refer back to this table when you're looking for, what are the antiderivatives of the pieces that you've kind of broken your integral into. All right, so that is it for this video. Like I said, tomorrow we'll be getting into some new methods for finding antiderivatives, and yeah, I'll see you then.